Running AI locally is not just a hobby anymore. It's something that forces you to understand AI deeply and fundamentally. And this is becoming a skill with an extremely high demand. Now, the problem is that we as software engineers have become a bit spoiled because a big part of software development right now has become just sending a prompt to OpenAI and your software is done. So OpenAI in this blue box hides all the complexity that you need to understand in order to be able to self-host your AI. And this is a bit unfortunate because I think what's in this blue box is one of the most valuable skills you can acquire nowadays. The problem is that as a beginner, you see terms like vLLM, GGUF, PyTorch, FP8, LoRA, MLX, and you get extremely overwhelmed. You don't even know where to start. So in this video, I want to show you the map of local AI. So we're going to create the layer map of local AI, understand all the building blocks and the foundation that makes up an AI model. And once we have this map in our head, we're going to be able to understand and assign all this terminology to the specific area they belong. And it will be much more clear in our head what is happening. But we're not going to look only at the building blocks of AI. We're going to look at the life cycle of AI, from pre-training it to running it and combining the map and the life cycle with AI. Everything will start making so much more sense. All right, let's start with the layer map first. And the first layer of the map is the architecture. Here we have something like Qwen, we have Llama, we have Mistral, we have GPT. And the architecture is something that defines, okay, how big the vocabulary is, how many hidden layers do we have in the neural network? Is that a mixture of experts? Is that a dense model? And stuff like that. Then we have the weights at the second layer. And those are actually the learned tensors that define the behavior of the network. The weights pretty much define the logic of the neural network. Then at the next layer, we have the tokenizer, and as a bonus, we have the chat template as well. The tokenizer tells us how to convert text to IDs because neural networks cannot work with text. They work only with numbers and matrix multiplications. So that's why we need to convert our sentence that we input into our LLM into an array of numbers. And this is something that the tokenizer does. And then we have the chat template, and we'll look at a concrete example later. What does that mean and why do we need it? Layer number 4 is the storage format, and this trips up a lot of people. Here we have things like Safetensor, GGUF, MLX, and we're gonna look later in more detail. In this part of the video, I'm just outlaying the map that we have. And later in the video, for every layer, we'll look at an example and it will become more concrete. Then we have quantization. Here we have different formats like FP8, BMB 4-bit, Q4KM, and those formats run in different runtimes like llama.cpp, MLX, or PyTorch. And I'm going to give you also a table cheat sheet so you can map quantization formats to the specific runtime they belong to. Speaking of runtime, the next layer that we have is runtime. And here we have different runtimes from enterprise to local runtimes, smaller runtimes, more portable runtimes, more enterprise-grade runtimes, runtimes that parallelize multiple GPUs, runtimes that can offload some work to the CPU. Yeah, just for different purposes, we have a lot of runtimes. On the wrapper layer, we have applications like Ollama, LM Studio, probably heard of that, OMLX for Apple Silicon. And then on the next layer, we have different optimization strategies. And you probably have heard about Unsloth here, which we are going to look into more detail later, what this company does. But for now, know that it optimizes the weights so they can run more efficiently. And then the last layer, I believe layer number 8 is the hardware. Here we have hardware like NVIDIA consumer hardware, RTX. We also have their enterprise chips, H100. And we also have Apple Silicon here as a last example, but there are, of course, other hardwares. And hopefully this maps gives you a bit of an overview of the foundation of an AI and what building blocks it consists of. So next time someone says, I'm running Qwen locally, this is not enough information in order to be able to evaluate what exact setup they have. Like one example of a setup that they could be running is a local map, Qwen3 model, GGUF file format, 4-bit quantization through llama.cpp as a runtime, and then wrapped in LM Studio on Apple Silicon. This is one way to run Qwen locally. But there are so many other ways to run Qwen locally. You can also run Qwen locally in a production grade situation where you self-host the AI on some company hardware. For example, you have Qwen running in Safetensor file format in an 8-bit precision via vLLM, and then you have the enterprise NVIDIA GPUs, which are super fast and super expensive. So when someone says, okay, I run Quant locally and I tested it, it makes sense to specify some of those in order to get more context around their setup. Now that we have the map of AI in our heads, let's look at the AI lifecycle. It consists pretty much of 6 stages. The first stage is the pre-training, where the architecture is decided, the tokenizer, and the base weights. The base weights don't encode yet the logic that you see when you chat with ChatGPT or when you have a coding agent. It's just an autocomplete. But in order to make this autocomplete more useful and to be able to help with coding or be a useful chat assistant, then you need to apply reinforcement learning in post-training. And the weights that are actually useful are the instruct weights, not the base weights in the pre-training. And then we have the chat template that is defined in the post-training as well. And I'm going quickly through the AI lifecycle because once we have this rough structure, we're going to start breaking it apart and actually look at examples, how a chat template looks like, how a weight actually looks like. And don't worry, I think this is something that everyone can understand. Then we have the release phase. All the artifacts are released on a Hugginface repository. We're also going to dive deeper and understand why do we need Hugginface exactly there. We have the Safetensor instruct weights, the configuration, the architecture, the tokenizers. We're going to look at concrete files. Then we have the conversion to the exact runtime that we actually need, GGUF, MLX, and other serving artifacts. Second to last step is the quantization. There we convert the weights to a smaller formats to save memory. And finally, we run the model in llama.cpp, LM Studio, Ollama, vLLM, or any other runtime. Okay, now let's start making things more concrete. I'm on the Hugginface website where usually open weight models are uploaded. And this is the model card of a small open weight model that we are going to look into. This is a SmolLM2. 135 million parameters. We can also see the model size here, as I said, 135 million parameters, and the tensor type. This is that each weight is saved into 16 bits, which is 2 bytes. And then if we scroll a bit, we can see how to load the model, how to run it through transformers and things like that. We can see the files of the model here, and we're going to inspect them. But first, why do we need Hugginface? Well, the reason is that when a lab releases an open weight model, we don't want every lab to release their own standards in their own format. So Hugginface standardized the way we publish open weight models. Every time someone wants to release an open weight model, they release it in this format. They release Safetensors in exactly the format that Hugginface wants. And that's pretty much it. It's basically standardization. And we said that in the pre-training, we defined the architecture and the tokenizer of the network. Now the architecture, for example, in this model is defined in config.json, and if we click it, we are already going to see a key architectures with a value, llama for casual LM, number of hidden layers, the size of the hidden layers. So everything you need to know about the architecture of the open weight model is in this file. So we got the architecture in the pre-training in the config.json, and we also said we have the tokenizer, and we also said that the tokenizer maps subwords tokens to number IDs. And this mapping is actually in this file, and the file is a bit too big to open it. So we're going to check the raw version, and you're going to see that every symbol, every token is pretty much mapped to a number. And that's what the neural network sees. And those files, config.json and tokenizer.json, are decided in the pre-training stage. Just to remind you, we are here in the pre-training. Now, in the post-training, we have a chat template and instruct weights. What does that mean? The chat template is in the tokenizer config.json. But first, why do we need a chat template? We need a chat template because modern LLMs are sensitive to the exact text they get. And when a user sends something like explain GGUF to llama.cpp, llama.cpp uses the chat template, which injects additionally your helpful assistant, and then forwards the whole prompt to the LLM. So the LLM doesn't actually see this part only. It also sees what the chat template has injected. And if we look at the Hugginface repo again, in the tokenizer config.json file, we can see the chat template is defined here. And you can also see those tokens. I am start system, your helpful assistant named SmolLM trained by Hugginface. I am end. And then the message of the user is injected. Now in the post-training, we also have the model weights the final weights, and those are in the Safetensor file, model.safetensor. This is a binary file. We cannot really see it. It's 270 megabytes, and you can click it. We cannot preview it because it's a binary file. It's a very large file, but we can at least see the structure of the neural network. For example, we can see that in the zeroth layer, in the attention block, in the projection matrix, we have a tensor that's 576 times 576. So it's a two-dimensional matrix. And we're going to look at that, by the way. I'll tell Codex to download those weights, decrypt them so we see the numbers and not the binaries, and we see that it's exactly one matrix like this. So what we're going to look at now is we're going to look at exactly this one attention block. As we said, this is actually just a two-dimensional matrix, and it's 576 times 576. And in each row and in each column, we have basically numbers that are weights, and those weights represent part of the network, and they represent exactly this part of the network. So I've asked Codex, so I just pointed Codex to this repository and told it to download this specific layer. And then I previewed it, and you can see that it's binary. So and then I asked Codex, hey, can you decrypt it so that I can actually see those numbers? And Codex said, say no more. And you can see that this is a CSV file that is decrypted for this specific layer. And I'm not sure if you can see it because it's very small, but here the number says 576. So we have seen that the exact weights of the model are on Hugginface, and that they are the exact shape that they claim to be, and that they're nothing else but numbers in specific matrices that are called tensors, which is the unit of computation those runtimes and inference engines compute over for efficiency reasons. So we have looked at the pre-training, the architecture JSON file, the tokenizer JSON file. We have looked at the instruct weights, the Safetensor. We have looked at the template, and we also understand why do we need Hugginface repository. It's a way to upload open weight models in a standardized format so the whole industry is aligned. Now, the problem is that not every runtime library understands Safetensors. So some of those need to be converted. For example, llama.cpp doesn't understand Safetensors. It has its own tensor library, which is called GGML. So that's why we need to package all those files in a single file, which is called GGUF. And to summarize, so the Hugginface repo contains all these files. They are usually well understood and well loaded by the enterprise grade libraries or the heavier libraries like Transformers and PyTorch, and then they can run on vLLM. So they can be loaded directly. But for something like llama.cpp doesn't target enterprise-grade deployment or speed at all cost. llama.cpp targets portability at all cost. And also it can offload some of the GPU work to the CPU. So it's built with a different purpose in mind. So it has a different tensor library. It has a different way of computing matrices. So it cannot load the model weights via the Safetensor files. It needs a GGUF file instead. So we need to do a conversion, and the GGUF artifact actually encodes everything what you see in those files, but it's a single file that llama.cpp can understand and can run. And in the llama.cpp repository on GitHub, let me see if I can find it, we can see a Python script that takes all those files and converts them to GGUF, so llama.cpp can actually run them. Now, if you look at our map, we understand pre-training, we understand post-training, we understand release, and I'm going to give you some cheat sheets so you can map GGUF to llama.cpp, MLX to Apple Silicon type of runtime, and then other serving artifacts. So none of these terms by the end of the video would be unfamiliar to you. Okay, let's talk about quantization a bit, and then I'm going to show you all the cheat sheets that you need to know. First, why do we do that? Imagine we have a model that's 7 billion parameters. This model roughly needs 14 gigabytes to fit into memory. And each weight of the model looks something like this. So the weight size is 16 bits, and we're going to say that it's like, let's say it's 16 bits. 16 bits, 14 gigabytes, right? And we have roughly 7 billion parameters. And the model size is roughly 14 gigabytes because we have 2 bytes times 7 billion parameters. It's around 14 gigabytes. Now we can halve the memory footprint with pretty much keeping the same precision of the neural network. How do we do that? We just take the weight and remove some of the precisions that, you know, intuitively this wouldn't change the outcome much because we have changed a part that is so minor that it really doesn't matter. But for that, we have saved 8 bits for each weight, which means that although the number of parameters stay the same, we now have a model size that's half the memory. We went from 14 gigabytes to 7 gigabytes. We went from 16-bit weights to 8-bit weights. And that's why we do quantization, because we can reduce greatly the memory footprint by losing just a tiny bit of precision. And it's very common that we run 4 or 5-bit quantization in practice. And speaking about quantization, something that you would very often see is this company, Unsloth, or weights that start with UD, which means Unsloth Dynamic, because this company is the first one that made, as far as I understand, the first one that made dynamic quantization actually popular. And it means that we don't reduce necessarily every weight to 8 bits or to 4 bits. We dynamically choose which weights are worth reducing and which weights are not worth reducing. So the company does dynamic quantization. Some of the layers would be quantized and some would stay as they are. And now that we understand Unsloth as well, it's time to look at the cheat sheets, which tell us which runtime runs which format. So if you see something like Q4, this means that it's 4-bit quantization, and M means this is the medium recipe. So we didn't run the highest quality algorithm. And this type of format is usually for GGUF, so you can run it in llama.cpp or Ollama or LM Studio. And if we go to Hugginface and click on the model here in quantizations, you would see so many Q4, KM, GGUF, because this is a very common quantization that you can run on a model. You could see GGUF, GGUF, GGUF. A lot of people just run llama.cpp. And here you have also MLX, which is for Apple Silicon. Now back to our cheat sheet, we see here UD, which is Unsloth Dynamic, which means dynamic quantization. But this can still run in llama.cpp because it's still GGUF. It's just differently quantized. Then we have more enterprise-grade formats, BNB 4-bit, AWQ, GPTQ, FP8. Feel free to pause the video and check out those tables. And here, again, table in a similar format. If you have Safetensors, it means vLLM, SGLang, MLX. The original release format, GGUF for llama.cpp, MLX for Apple Native, and then AWQ. And lastly, the runtime cheat sheet. Local chat on a Mac, LM Studio, Ollama, LMX via LM Studio. And I don't want to bore you with all of these things, but I told you by the end of the video, you will understand all those terms that we have here. And if you don't understand any of them, you can just look at the cheat sheet and map them. I don't want to waste your time if you're not interested, but I think we have covered pretty much all of them. We have covered the map of AI, we have covered the lifecycle, and we have covered the cheat sheets. I hope this video was useful. Thanks a lot for watching and see you next time.